Alright, I think it's about time we get started. Let me make sure that OBS does not crash. Oh no. Okay, sorry, my audio was playing. The B in black hole stands for scuff, so it's all good. Oh, did that work? Oh my god, I'm like 4 frames per second. Oh my god, I'm very laggy. I think it's good now. Okay, Speeding at Sea, it's me, Z. Hello, everybody. I hope everyone is doing all right. It looks like I am still moving at like 4 frames per second, but maybe it'll be a little bit better if I adjust it like this. Whew! I hope everybody is having a spectacular day. So my voice is in good condition, but it's still a little rusty. If you guys don't know, I had to delay the stream from yesterday because I was feeling a little bit under the weather. I still sort of am, but my voice has been getting a bit better, so that's great. So I'm gonna do a quick roll call, quick attendance. So if you're here, Orbeez, say here, and I will mark you present for class and give you a little A in the grade book. Hello, Eggy. Hello, Brenda. Hello, Stella. Hello, Urist. Hello, Astral. Hello, Apa. Hello, Tack. Hello, Arky. Hello, Supermoki. Hello, Zilla. Hello, Warpy. And hello, everybody. I hope everyone is having a great day. I don't know why I'm still moving at like 4 frames per second. Let me see if I can somehow try to like magically fix that. As you may know, I have a lot of windows open and my laptop sometimes is not very good with having a lot of tabs open. I think this should be all right. Yeah, I think it'll just be like this for a little bit. Hopefully it gets a little bit better. Hello, Large Hadron. So I've been traveling. I think even saying traveling is a bit of an understatement because I have literally been speeding at sea. Uh-oh. Oh wow, okay, I'm really lagging out right now. It's okay. It's very scuffy today. I have been traveling and I am actually going to be traveling again in roughly 2 weeks. Here's a hint, I'm going to a nuclear fusion facility. So that's going to be a lot of fun. But I've been having a lot of foods right now. Yeah, having a bunch of tabs open just gobbles up RAM. Yeah, I think that's the case, because I do have quite a few open, including some of these research papers and stuff like that that I wanted to show, so hopefully it'll be alright. Yeah, no, nice. Yeah, no, it was great. I had a lot of oysters. I tried olive oil ice cream for the first time. I don't know, Orbeez, have you guys tried olive oil ice cream? I went into it thinking it would be nasty, but I was actually really blown away. It was really, really good. And I, of course, had a lot of Zoffy. And right now, too, I wanted to feature my, my giant Zoffy cup, because this is roughly equivalent to how much Zoffy I drank today. Trying to stay alive. I think I've been drinking also warm coffee as well to help with my throat, which is already starting to thin out a little bit. Yeah, so I came back from not vacation, I've been working. I came back from my trip, and I was flabbergasted by the VTuber tea that has been taking place in the community. And I heard about this quite late too, so I was like absolutely blown away. I'm still not up to date on like everything that happens, so if one Orbeez has like an update, like a summary of what went on, like please send it my way. From what I understood, there was like Iron Mouse's like announcement, which I watched and was absolutely flabbergasted by, and then like I think there were some other things with a few other like VShojo members all leaving the company. Anywho, it's been absolutely crazy. Olive oil ice cream. I never thought I'd hear those words together. Yeah, no, me neither. And it had caramel in it too, but it was actually very good. I think the caramel gave it some sort of sweetness that helped the olive oil ice cream come together really nicely. Smallest cup of Zoffy. Alright, is this more accurate? Is this more accurate? I think that's more accurate. Here, let me try to close some of my windows. I have this really nice, like, black hole background going on. I think I'm gonna close that. I think that's actually decreased my frames per second. Oh dear. Now it is medium-sized. Like, typically it's this big. Can you Orbeez even see me through this Zoffy cup? There needs to be a Chibi Z in the Zoffy cup. I'll add that too. Let me look for a Chibi Z to add into this coffee zup. Coffee zup. I meant Zoffy cup. As you always can tell, I'm still feeling a little bit under the weather, but it'll be alright soon. Yeah, no, I'm at least lucky that what I have right now seems to just be like a mild cold, and I've just been working from home, because some of my colleagues' friends are doing these like viewing nights where they have to stay up from, I kid you not, 10 a.m. to 4 a.m. And we were talking about, like, if one of us gets sick, it's like, it's over. Like, it's over. The Zrain Zot is zroing, yes. In its natural habitat, the humble astrophysicist can consume its entire body weight in Zoffy in a single day. I can attest to that. But I've been trying to actually reduce my coffee intake. I've been averaging like 2 cups a day, so. Ginseng tea is the best. I'm actually drinking this Korean tea that was gifted to me. It's some sort of special, like, it's called wedding green tea. I don't know why it's called that, but it's very sweet. It sort of tastes like peaches. But yeah, anywho. What other things? Oh, one of the things I'm doing this week, if you guys are fans of like Buffalo Wild Wings, is I heard that Buffalo Wild Wings has infinite appetizers. Like, until like August or something. Like, all you can get appetizers. And I'm trying to see if I can tap into this lucrative opportunity, because this is like crazy to me. So that's gonna be a lot of fun. But I think this weekend I'm gonna try to take a little bit easy, try to recover. Oh, one thing that I'd love to highlight is there is one exciting update, which is that I am collabing with, OMG, let me pull this up. I'm collabing with Millenium this upcoming weekend on Sunday. So we've been like brainstorming ideas for streams, and we finally agreed to do the trolley problem, because we were talking about things, because she also does like a bit of science content, and I was telling her that like I do like physics and that kind of stuff, and then we were like, you know what could really bring our communities together? The trolley problem. So you guys better be there for that. It's actually going to be an early morning stream at Pacific time, so this will be a great opportunity for you European folks to not have to like stay up to watch my stream. It's gonna be, I believe, at 9 a.m. Pacific time on Sunday. So that's gonna be a lot of fun. It's gonna be so I'm gonna stream, and Millenium is also going to stream, but the game will be hosted by her, and I'll kind of just be spectating and helping out. So it's gonna be a lot of fun. Yeah, Millenium collab, let's go. Yeah, no, it's great. It's great. A lovely late afternoon. Yeah, maybe for the European folks. I know that some of you Orbeez have wanted me to do morning streams, so this will be a great opportunity for that. This collab has, I kid you not, been like months in the making, so I'm really excited to show you guys like what I've been working on. So it seems like my frames per minute is like not improving, so I'm gonna just quickly like try to force quit some of my apps. So I will be right back because I don't accidentally want to dox myself. Let me force quit that. Let me force quit that. Okay. Let me try going back. Oh. Oh. I wonder if that helped my frames per second. I don't think it has! Orbeez, this stream is so scuffed. Yeah, it's short hair Z in the thumbnail. Yeah, I wanted to switch it up. I also wanted a shock thing. Hello, Chili Shot Orbitus. Sub straight away. Thank you so much. I love your name because the fans are called the Orbeez, so this is great. Yeah, no, the scuff is just getting worse. I don't know what's going on. I'm trying to figure it out, Orbeez, please. Maybe if I restart my thing? Yeah, you know what? We're gonna just deal with it today. Sorry, I don't want to spend way too long on this. But yeah. Maybe the black hole background? Actually, you're right. Maybe if I... Oh! Oh! I can't see that notification because the thing is blocking it. Thank you, Orbitus, for subscribing. Here, let me actually delete my other background. Oh, I think that helped a little bit. Anyways, we'll deal with it later. Wife, thank you. Well, we're gonna start reading, yeah, so all these black holes have been consuming my CPU, which means that it's probably about time for us to start reading about this. So I actually have like quite a bit of notes here to explain like what's going on here, because this is like super exciting, and I really wanted to showcase this paper. So, you know, typically I go for like Astrobites and I try to make it a bit more accessible. This time I thought it would be better just to read the paper straight from the source and just check it out from there. So again, if you guys have like any questions, like please don't hesitate to just stop and interrupt, because I am really happy to answer any questions to the best of my ability. I'm also going to replace the chat with the smaller ones so that you guys can actually read along with the paper. Yeah. Yeah, there we go. You guys are gonna move to the coffee cup, actually. I think. Does this work? Is this too small? I'm not sure if this is the... I'm not sure if this is the best thing. Orbeez, this is, I think, like, the most scuffed stream I've ever had. I, like, kid you not. Please, I just want to resize this. Please. OMG. Alright. Okay, I'm gonna try refreshing that. Okay, I think that's a little bit better. How does that look, Orbeez? It's a little cut off. I guess it's also not catching up either. Orbeez, please! Okay. Oh no, I accidentally deleted the coffee cup. Orbeez, this is the most scuffed stream I've had. Okay, it's okay. It's okay. We're gonna make this work. We're gonna bring the coffee cup back. Oh my god. Orbeez, for those of you who are new here, I promise you, like, my stream is not typically this scuffed. Okay, we're gonna do this. Alright, I think this is actually great. And everybody can see this. That's actually better? Yeah, no. Let me make the chat a little bit darker too. All right, I think I did it. OMG. Just needs to bring the chat back. No, this is great. I think this looks great. The chat just needs to catch up for a second, I think. You're doing great. Thank you. Thank you, Yvonne. Welcome to the stream. I promise you my chat is not like this. Hello, Jambone. Hello everybody who is new to this channel. This emoji is literally me. What is the coffee cup for? I'm like still mildly sick from traveling, so I've been consuming a lot of Zoffy. Alright, I think this is in a good state. Alright, without much further ado, let's talk about black holes. So this is not a black hole, but rather a really cool gravitational wave event that was detected by LIGO, by Virgo, and the Cagra collaboration, as it's written here. This paper has been basically everywhere. People have been talking about it. It's been genuinely like really exciting for the astrophysics community, and I hope that you guys have also had a chance to like hear about it in like popular science and that kind of stuff, because it's been very everywhere. Z, just FYI, we won't go mad if things go wrong. Thank you so much. I promise you, my streams aren't usually this scuffed. So the reason why this event is so exciting is because from measuring this event on November 23rd, 2023, that's why it's called 231123. That's literally the date of the event. After measuring them, they determined that this gravitational wave event occurred from the merging of two black holes, which is typical for these very high energy events. But what's surprising is just how massive these black holes are. And so in the news, they've been calling it like the monster black hole merger event, because it literally is a monster. And I'll go a bit more in detail in just a second. Yeah, never heard of it. Yeah, this has been going around the scientific community, but of course, like, it's not like, you know, if you aren't really as involved or like not on like popular science media, it may have been a bit hard to hear about it, which is why we're covering it. It's super exciting. So I just wanted to like just start off and like go through like, okay, so this is the event that they measured, right? Like it's this like weird like sinusoidal looking thing. And this is what gravitational wave things look like. Like before the two black holes are coming together and they're like going like, and they're going together, and then they like merge, and then they have these like big oscillations and a giant release of energy as shown here. But one thing that I wanted to point to, this paper is really great, but maybe a little hard if you haven't really read astrophysics papers before, is just this table. So this is basically the source properties, which means properties of the two black holes that merge together of this gravitational wave event. Is this the thing we built the massive X lasers for underground? Well, yes, this is LIGO, which is basically an L-shaped system. So let me see if I can try to get a photo real quick. I think I actually saved one in advance. Yeah, so... Oh, this is humongous. Please, scuff. So this is LIGO. This is the detector, and it's L-shaped. And so you might be wondering, oh my god, it's huge, why do they do that? And the reason for that is because these lasers are shot out. And at this center region, they determine the time it takes for the laser to shoot out and come back. And they do it for both sides. And they measure the time, the difference in time of arrival. So you might think, oh, it would just be like the same, right? No. When a gravitational wave event happens, the space itself is actually like smushed and distorted. which leads to the time between these like two events not being the same. Yeah, this is only one of them. So yes, they have two detectors. So basically two ways of confirming that this event has taken place. So that's why they have, I think that's, yeah, they have two signals here. So they have one in Hanford and one in Livingston. Let me check which one is, I think yeah, so there's one in Louisiana. I'm just gonna quickly check where these are because, yeah, there's one in Louisiana and there's one in Washington. Okay, that's what I thought, but I just wanted to confirm. Yeah, so Hanford is in Washington and the Livingston one is in Louisiana. So LL, very easy to remember. And they both look like this, and they both offer ways of confirming whether these events happen. Yeah, basically just like time anomalies. Well, the thing is, there are a few other detectors, but if I recall correctly, Virgo wasn't on when this happened, so there could have been more ways to confirm, but for now, this is all we have, these two little chirps here, and I'll talk a little bit more as to why, you know, we should have another detector on and so forth, because I do have some opinions about this. So, this is the source properties, which basically describes what are the properties of the black hole itself. The black hole mergers. And they claim that one of the black holes is 137 solar masses, and the other black hole is 103 solar masses. This is insane, because prior to this event, the largest black hole merger that was detected by LIGO was like 140 solar masses combined between the two black holes. And now this is what, like 240, like this is like 240 like solar masses combined, which is crazy. That's almost like twice as much as what we've detected in the past. And the reason why this is like important is because these are known as intermediate mass black holes, which is this like region where we don't really quite understand how these black holes form. The final mass is smaller. Yes, the final mass is smaller because some of that mass is released as energy, as the gravitational waves. So that is later like what we measure. So of course, like this difference in mass from 238 to 225 is that energy that is released. Was the method the same for the previous black holes? Yes. They were both detected by LIGO, which is like our primary detection system. Like, I think like before we thought that other black holes could have been in the intermediate range, but like this is like definitely within that intermediate black hole range. So you might be wondering like, what is this intermediate black hole thing? Like, why is it important? So we have some theories as to how massive black holes formed in the early universe. One possible option is that like, sorry, I'm reading chat and I'm unable to think while talking today. Yeah, it's like 10 suns worth of gravitational waves. Yeah, no, it's a lot of energy. It's absolutely impressive. Yeah, so Mini Art says, we're talking about the total amount of matter, but not necessarily the volume. They may be 238 times the sun's mass, but not 238 times larger in the sky. Yeah. And one thing to also consider is that these are black holes. So when they merge, like black holes are technically singularities, so they don't really take up like volume in the sky. Around black holes, they have accretion disks. And you might be wondering, what does that look like? that looks like this thing like around the black hole. And that could also increase as well. Yeah, no, it seriously is a lot of energy. Anywho, one other thing that's really interesting about this is that these black holes are spinning really freaking fast. So these units might look a little bit weird to you. You might be like, oh, it's like a decimal. That doesn't sound very big, right? Well, these are decimals. And you can think of the largest spin a black hole could possibly have as 1. So that means that the final spin is like almost 1. Like it's spinning like super freaking fast. And before, the black holes were at 0.9 and 0.8. Which is insane. Like that means that they're basically both like incredibly fast spinning black holes. And they merge to also become a very fast spinning black hole. It's relative to yeah, it sort of is. I think if I recall correctly, it's like some sort of general relativity unit related to like calculating MC squared. So yeah. So it's also weird that these black holes are spinning so fast because it's hard to gain a lot of angular momentum like that. And the fact that they also merge to have a very high total spin at the end means that the black holes must have been aligned in a way that's like really challenging to imagine. Oh, thank you, Silo, for stopping by. Oh yeah, the GIF is great. Yeah, it's just me typing away. Is it the black hole spin? Black holes themselves can spin, and the stuff around them is also spinning as well. I'm actually curious how they measured spin magnitude. I'm actually curious. I'm gonna try to see if I can search this up. How they calculate. Let me see. So the question is, how is spin magnitude calculated? And is it only the black hole part that is measured? Who wants to drift a forklift with me? I am casually forklift certified, not officially. So it's rather the spins of the individual components. That doesn't really answer my question either. Oh, they have to do some sort of Bayesian analysis of the gravitational wave signal. So the gravitational waves carry information about the masses and the spins of the black holes. Yeah, it's extracted from the gravitational waves. So guys, right? Yeah, so I'd say roughly 5% of the total MC squared of the system is radiated away. It's weird because if you'd imagine two randomly spinning objects, how is it possible that the final combination of the two has big spin? It's really interesting. I'm looking at my notes to make sure that I've said everything. Yeah, but one of the other reasons why this intermediate black hole collision is so important is because we've been trying to look for evidence where very high mass stars become black holes and they merge together. So one of the questions that we have from looking at the earliest black holes is that we're noticing that black holes are a lot bigger in the earlier universe than we could have imagined. And so there's two ways of sort of thinking about how black holes merge. The first is that two stars die, they both become black holes, and they merge together. So the two stars were next to each other in the first place. They formed together in the first place. then the second possible way is that these stars weren't born together, but rather they're part of this giant star cluster, and they came together by being gravitationally attracted to one another. That's another option. And the fact that we've seen now 2 intermediate black holes merging is an indicator that we can have multiple generations of mergers. As in, like, we could have like small black holes merging together, and then they merge with bigger black holes, and they merge with even bigger black holes, and they become even bigger throughout the process. And this is basically confirmation that this could be the case. Now, of course, that being said, like, there's a lot of caveats. These little plus and minus symbols around here represent the errors. And if you look here, like, the error is like humongous. Like, it could be for the second black hole, it could be 123 solar masses, or it could be 50 solar masses. So there's a huge range as to what these errors could be. In addition, for this spin as well, like, it could either be 0.92, which is like spinning heck fast, or it could be like 0.6, which is not fast at all. The black holes are playing Agario. No, exactly. Like, that's literally like what could be happening right now. So this is basically the strongest evidence we have of like potential hierarchical merging, which is what this process is called. The black holes playing Agario. So another thing I also wanted to point out before is this thing right here, right? What's really sad is that we basically only have like, what, like 3 or 4 oscillations? And that's like barely enough to understand like what's going on here. And basically we're getting all of our information about the system from these little like 3 to 4 oscillations. And so there have been a lot of scientists calling for getting lower frequency instruments where we're basically detecting these like little wobbles like right before the main signal itself. And these can give us clues as to the gravitational interaction of the black holes as they orbit one another and before they actually merge. So that would help us constrain some of those huge error bars that we saw earlier, which is great. What impact would the merging of black holes have on the understanding of the origin of the universe? Well, not necessarily the origins of the universe, like the black holes, like the Big Bang Theory in itself is like very, very like well established. But one thing that it could indicate to us is how the first black holes formed, obviously, and also how the first galaxies formed. Because black holes, we have supermassive black holes at the center of galaxies, right? And they basically interact with the galaxies and can turn on or turn off the galaxies, which means that they can lead to stars that are forming, or they can kill a galaxy so that there's no stars forming at all. And this interaction is incredibly complex. So understanding the first black holes and how they grew and how they interact with galaxies can give us some indicators into how galaxies formed as well. And understanding basically the properties of the early universe. Do black holes have polarity like a magnet? If I recall correctly, yes. Well, yes. But the extent to which like black holes have like magnetism or polarity depends on the black hole itself. Yeah, I just quickly searched this. Yeah, the black hole, like, well, okay, let me clarify. These black holes have very intense magnetic fields, and they're powered by accretion disks, which is the disk that goes around the black hole like this. Now, this just looks like a cloud of stuff like going around the black hole, but it is highly energetic because it's like superheated plasma like spiraling into the black hole. And that superheated plasma has charged particles. And when charged particles move around like that, it generates magnetic fields. And so we do see sometimes like highly energetic jets with strong magnetic fields. So Ton 618 could be like an Agario super veteran. Lamau, that's one way of putting it. So Ton 618, I think it's like the largest black hole ever discovered. Yeah, it defeated Agario. I wish I understand, but I'm nodding along. Well, feel free to answer any questions. I hope I'm not going too fast. Basically, giant black holes collided and merged, and this is super, super exciting because it could tell us a lot about the earliest black holes made in the universe. Oh yeah, I guess I did want to look at one other plot in the appendix. Was it this one? Wait, I'm gonna quickly check if it's in this paper. I thought it was near the end. Yeah, I think it's this. So one of the things that, yes. So one of the things that this paper also did is you need to extract the information about the black holes just from those little wobbles that they measured, right? And so to do that, they actually simulated the black hole mergers themselves. And from that, they were able to roughly extract and simulate what the merger would look like and try to match it with observations. Oh, how did they extract the numbers from the waves? Well, okay, so that process is like really complex. Like the process itself is like, they do a lot of like Fourier stuff, but one of the things that they do is that they have these like waveform approximants, which compare, like I mentioned, they basically model these different like black hole collisions and try to see what matches the best. Yeah. But what's really interesting about this plot and why I wanted to draw attention to it though, is that basically they feed the simulation a bunch of information about the two black holes that are coming together, and the simulation spits out what it thinks the gravitational waves would look like. And so for some of these things like this, like you can see like just from the top that all of these like different simulations line up. But sometimes it like doesn't line up at all. And that's because of the incredibly high spin of the system. And because of the high spins of the system, it's really hard for us to model what this collision would look like because we've never seen anything like this before. We don't have very much data on how two black holes with high spins coming together should even look like. And so our models are kind of all over the place. I think there was a better version in the appendix of a version of this paper that kind of goes over this in more detail. But it also comes to show that like not only do we need to do a better job observing these events, but observing more of these events can help us understand how to improve our simulations and predict the properties of these events as well. Did they look at the polarization of the gravitational waves? Let me see. Page 9. Let me look at this. So if we, oh, oops, wrong tab. So at the top of page 9, that the DSN model yeah, they assume polarized waves. I mean, I'm sure that polarization is like a feature of this simulation itself. So they considered it, but I don't think that was a main focus of this paper. Hello, Ina. Or Cleonium. what's crazy to this, for this as well, is I want to put this in context for other gravitational wave events. In the past, we've detected gravitational wave events, like there was one called like 150914, and it only had a difference of 3 solar masses. So it radiated 3 solar masses as gravitational waves. And because we had more detectors on, we were able to constrain where the event was located. Unfortunately, I don't think they were able to determine where this event located, but for that other event in 2015, they did. And for that event, it had 50 times the luminosity of all of the stars in the observable universe, which is wild. And that was for a difference of 3 solar masses being radiated out into space. They're claiming now that we're radiating 13 solar masses into space. And it's faster because they're spinning even more faster, so you can imagine like how crazy this event is now. So I was also like curious as to like, they've detected this event in 2023. So how come it took them so long? Well, I think if I recall correctly, there's this like catalog paper for this thing called Journey coming out soon. So there have been a lot of like publications that have been scrambling to take place, and this was one of the things that they announced. But it's like super, super exciting. Like even just from this, even if we were to exclude the mass and just look at the spins, the probability of a black hole system having this fast of a spin is like very slim. So that's also exciting for this as well. If we had a neighbor black hole, well, I don't think that would be very pleasant, because a neighbor black hole would produce a lot of radiation. I mean, we would be able to do all sorts of experiments. We'd be able to track the radiation. We'd be able to understand the anatomy of a black hole better. All these different things, which I'm actually going to cover next, because I wanted to go over this really great review paper by Astrobites. So it's a little bit more lay friendly, explaining how black holes work. Hello, Kraken. Great to see you. I'm going to take a sip of my tea because my voice is like definitely going out. Whew. Yeah, make sure to stay hydrated, Orbeez. Cool. So let me just quickly go to the next thing. I think today's stream might be a little bit shorter because I'm already noticing that my voice is going out. In the meantime, let me also pin this to chat so you guys can have that. Oh, actually, I think we should read this too. I really love this article. If we had a neighbor black hole, if the sun became a black hole, I don't think that would be very pleasant. Maybe we can just bring over a black hole, who knows? That would be great. So let's quickly read this. Heaviest black hole merger flouts a forbidden gap. I think this will do a better job than I did explaining how this works. Let me like zoom in a little. Okay, there we go. The largest to-date black hole merger is making headlines and defying astronomers' expectations. The record-breaking event involved black holes with masses around 100 times that of the sun, a range where the conventional formation process of stellar collapse is deemed impossible. So that was what I was explaining about how we don't know how the earliest and most massive black holes formed. The new observations suggest that some black holes formed through a multi-merger scenario. Basically, the black holes are playing Agario. Actually, Orbeez, if somebody can make an Agario like photo of black holes coming together, that would be hilarious. Or maybe with the membership icon, because I know some of you guys are black holes. Since the first merger detection in 2015, around 300 black hole mergers have been observed. Through this collaboration, which is a network of scientists operating gravitational wave detectors in the US, Europe, and Japan. When two black holes spiral into each other, they create ripples in space-time that can be recorded on Earth with highly sensitive interferometers, like LIGO, which is basically the L-shaped detector that we saw. Most of these black holes tip the scales at around 10 solar masses, a size that can be explained within a scenario where a massive star runs out of fuel and collapses into a black hole. So this is what we typically expect for smaller black holes, but not all stars have this fate. Very massive stars around 200 solar masses are unstable, according to the theoretical models. The energy within the core of such a star would be so high that it would produce electron-positron pairs, a matter-antimatter combination that reduces the star's self-sustaining pressure. The drop in pressure leads to a destructive implosion. The implication is that stellar collapse cannot produce. So this is sort of what's called an intermediate range black hole. It's sort of the forbidden gap in black holes, because a star dying can't produce it. So it must form through another way. In 2019, the LIGO Virgo Cagra collaboration detected a merger of black holes whose measured masses were at the lower end of the gap, and this surprising observation led to speculations about alternative black hole formation scenarios. But like this 65 and 85 were on the lower end. What's really exciting is that this new event is like definitely within that intermediate black hole range. Observed in November 2023, the signal was also short, just 1/5 of a second, which is crazy, just being able to capture that for such a brief period of time. The best fit turned out to be a merger of two black holes with masses of 103 and 137 solar masses. Because of the signal's brevity, the researchers could not pinpoint the location in the sky, which kind of sucks, but... So, how can these glides form? A possible scenario is that these black holes originate from hierarchical mergers, which is the Aquarium model, assumes that earlier generations of mergers create highly massive black holes that go into merge with other heavyweights. It's like a family tree of black holes. Normally, a merger event gives a recoil kick to the final black hole, which causes it to fly out of star-rich regions. A possible clue related to hierarchical merging is the rotation or spin of the black holes. Yes, and so it's really exciting that the final black hole has a relatively large spin value. That's because it essentially assimilates all of the angular momentum from the rapid orbital motion of the black holes. Yes, and although the values have very large uncertainties, these objects seem to be spinning near the maximum allowed values, one at 80% and one at 90%. Which indicates that these black holes themselves were also created with previous mergers. But yeah, there's a lot of errors here. So that's basically I just wanted to skim over this article. It does a really good job of explaining like what's going on here. And this is like super duper exciting. So yeah. Agario is a black hole simulation. Well, maybe if we have some time at the end, maybe I should just play Agario. So intermediate black holes cannot be created from supernovas. Yes, that's correct. Intermediate black holes can't be created from supernovas. So that's why scientists are proposing that there needs to be another way. Somehow that the black holes like came together, like merged together, like Agario. So let me quickly just close these real quick. Maybe we should go over this one. So I just wanted to go over an Astrobites paper. So for those of you who don't know, Astrobites is a really great way if you are curious about getting into reading astrophysics research. They basically take existing research and they sort of simplify it down so that anybody can read it. It's like a lay-friendly translation of a paper. What if they are primordial black holes? See, that's sort of another bucket of worms because primordial black holes are this like really interesting concept and it's just very hard to prove because those primordial black holes would be very small and faint and really hard to detect. Don't celestial bodies spin and merge and crash into each other? Yeah, honestly, sometimes the right explanation is the simplest explanation, which is why this idea of like hierarchical merging or like the black holes coming together has become like an increasingly like prevalent idea. I also realized that my laptop was not charging. So let me do that real quick. Okay. So I wanted to read this really quick paper that kind of takes like black holes in a different light. It's called On the Straight and Narrow, How Black Hole Seeds Agree with Scaling Relations. And it sort of goes into this concept of how black holes evolve. So let's just take a quick read. This is great. Oh yeah, no, this is great. All right, so astronomers believe that nearly every known galaxy... Oh. IP says PBH are also be on the screen to pay my friend money. Oh yeah. Well, if you don't mind me asking, like, feel free to also send it. If it's doxable, like, don't worry about it. But I'd love to take a read. And of course, if you guys also have other papers or comments or suggestions, like, please don't hesitate to let me know. I feel like that's what's great about the scientific community, just like reading more about these papers and just encountering papers along the way. Like today, I encountered a paper on Milky Way streams that I could have never like found, except that it was in like this like random like Slack channel. So basically like Discord, but for scientists and fancy people. It was like in this random Slack channel that I had never opened. And it was like really, really cool. It was about how a lot of stellar streams are disrupted and the possibility for the Rubin Observatory to detect a lot more of these streams. So I was really intrigued by that paper. So feel free to send anything that you encounter. All right, so let's quickly read this. So astronomers believe that nearly every known galaxy contains a supermassive black hole at its center. This is a black hole, an object so dense that even light cannot escape its gravitational pull, that is at least 1 million times more massive than the sun. That is crazy. As astronomers are using state-of-the-art telescopes like JWST to peer back into the first billion years of the universe's history, we observe that supermassive black holes already exist at these early times. And this is really surprising because it's not clear how black holes that massive appear that early. This depends heavily on how the black hole was formed or seeded. Yeah, so seeded is just like a fancy way of saying that. I think Nep would really like that phrase. There are two main ways in which we believe the seeds of supermassive black holes may have formed. First are the light seeds, which are thought to form from the deaths of the first generation stars. So that basically means a very massive star dies, and its core collapses, and it leaves behind a black hole. The second are heavy seeds. Oh, wait, I just said that. Maybe I got that wrong. Oh, I guess, like, these are the deaths of the first generation of stars. But, if I recall correctly, this is very challenging. I guess I'll go through that in just a second. So the second are the heavy seeds, which are thought to form from the collapse of very massive stars in the early universe that could form under special conditions. In short, a galaxy normally forms when the gas collapses and forms stars. However, under certain conditions, it may be possible to prevent the gas from fragmenting, which instead leads up to a buildup of gas at the center. So if I recall correctly, this first option that is talked about is kind of challenging because it would require these stars to be like gaining mass uninterrupted for hundreds of millions of years, which is very challenging, especially when the early universe was more disruptive, it was more active. And so this idea of these like heavy seeds could also potentially be more prevalent. So I don't like really how they explain this. So I should think of light seeds where a star dies and creates a black hole. Heavy seeds are where giant gas clouds sort of collapse to form a black hole. So these black holes are directly collapsed from gas clouds. And this is a better idea because it needs less growth and all the material is sort of surrounding the black hole already. And it's easier for these black holes to form from these gas clouds because sometimes when you have a lot of intense radiation, like intense ultraviolet radiation, it prevents these clouds from fragmenting and basically allows like one black hole to accumulate a heck ton of mass. The light seeds are me at the gym. No, don't say that. No. Well, these black holes are trying to bulk too, I promise. Someday I'd like to write a mock paper just for fun and to learn. I'd like to some peer review help when I do it. Yeah, no, that's amazing. Actually, that actually is really funny because me and Kim, who is also an astrophysicist, does very different work from me though. have been trying to plan another collab before I'm on break in August. And we were thinking about doing a stream. Okay, so if you've gotten to this point, I'm just gonna spoil it. We were thinking about doing a stream where we write a fancy, like, very silly, like, research paper together on stream. Like, using LaTeX and everything like that. Like, formatting it, like, really fancily. And we thought that would be a lot of fun because, I mean, in one ways, it's also a learning experience, right? It helps, you know, helps you guys see what it's like to write a research paper. And on the other hand, it's a lot of fun because we get to be silly and not have to, you know, stress writing that. LaTeX for the win. Yeah, no. Yeah, sounds like fun. Yeah, no, we're in the process of brainstorming this together. Yeah, it's been a lot of fun. Oh, YouTube chat prevents it? Well, feel free to sign in the Discord. And if you aren't, here's the link. Yay, okay, I was worried Stream Elements bot would also be borked today. That would be amazing. Yeah, so, Pepito, or Josem, if you want to, you know, that might be a stream you might be curious to visit to see how we structure our papers and how scientific writing really begins. I promise you it's not as serious or as scary as you might imagine. Give a read for RFC 1606. What is that? Oop. That's cool. I will save that for my to-read list. Yay! Yeah, no, it's gonna be great. Alright, so let's keep reading. So why is this all important? The mass of a supermassive black hole is known to be correlated with the properties of its host galaxy, or the galaxy at which that black hole resides, like the mass of the galaxy and the stellar velocity dispersion, which they give this like really fancy definition. Basically, it means like how fast the stars are zooming around the galaxy. And that's all determined just by the black hole at the center. So the black hole at the center might be this like tiny little thing, but it determines so many properties about the galaxy, including how much mass it is, how much star formation is going on, and so forth. So by looking at how the early black holes and their host galaxies compare to this relation between the mass and the speed of the stars, the authors can study how different models of these early black holes match observations. So they're looking at this special relationship between how much mass a galaxy has and how fast its stars are moving to try to understand what the earliest black holes will look like. So the authors use these simulations called Brahma, which are these magnetohydrodynamic simulations. Basically, they're simulating black holes, and they consider heavy seeds which form under the following conditions. So there's a lot of details here. But the reason why this is important is because they have 4 models. All models use the first condition that the host halo must be of a sufficient mass. And basically, as the models increase, they become more and more restrictive. And so these conditions determine how the earliest black holes form in their simulations. And so they're basically testing on these different conditions. And when they match the observations, that means that that condition must be correct to what we see in the universe. So tests of these different restrictions can determine how they impact the formation of heavy seeds or the early black holes. So first, they look at the overall population of black holes produced by each of the seeding models or the black hole formation models. And this first figure, which I'll show in just a second, shows the number density, so the number of black holes for the different models, compared with different simulations. So this pink one is another simulation, and B1, B2, B3, B4 represent their simulations, which have become increasingly restrictive. And so they notice is that when they have more restrictions on their model, they have fewer earlier seeds. But what's really exciting is that they can look really far back in time. So this thing on the x-axis is redshift, which is basically a measure of cosmological time. So the more further along you are here, like the later in time you are. And this is like basically the earliest black holes that have ever formed. compared to this simulation, which only goes up to like here, right? Redshift 9. They are able to expand and look at some of the earliest black holes in the universe. Is it just pure Monte Carlo simulations with fine tuning? I'm not sure if it's Monte Carlo, definitely, I guess so. Like they're doing some sort of like numerical methods where a lot of the ways that these hydrodynamic simulations work is that they're basically doing, they have a set of initial conditions, they have a set of equations that they know govern the behavior of black holes or matter or gas around these black holes, and they basically progress in time and evolve these equations. I'm not sure if they're using the Monte Carlo method specifically, but I presume so, frankly. So just to move on, they then look at this relation between the mass of the galaxy and how fast the stars are moving, and they find that in general, the less restrictive seeding models tend to produce larger black holes, which is great because we are noticing that there are observations of black holes in the early universe that are larger than anticipated. So the fact that they're less restrictive models are reproducing these massive black holes is great. Another important feature is in the evolution. The less restricted models tend to evolve less over time, particularly at lower masses and velocity dispersions. This is because the growth of these black holes in these cases are dominated by mergers with other black holes, whereas the growth of more massive black holes is dominated by gas accretion. So they're claiming that for lower masses, these black holes come together from like the Agario thing, where there's a bunch of different black holes coming together. And so they evolve more slowly for this relation of stellar mass and velocity. On the other hand, for more massive black holes, they have a steeper slope. And that's because they tend to grow from eating more of the material around them. So what's really exciting is that they basically compare these different models and look at these different black holes and black hole masses and try to compare the two. And they find these differences in the low mass and the higher mass regime. The Agario model, yeah, exactly. Wouldn't that be continuous physics based? Continuous physics based? I'm not sure what you mean by continuous physics based, but if you mean like, you know, going through time and evolving these like differential equations, then yes. Black holes are actually VTubers and their communities. Yeah, they're merging. It's just like how V theorem is like a combination of like all 5 of our communities now. Oh, and speaking of, I know there's some new people in the chat, by the way. If you don't know, I am actually part of this group called V Theorem, which is a bunch of like scientific communicator VTubers. All of our channels are there, which is great. So in summary, the way that the seeds of black holes are formed can have significant implications for where massive black holes and their host galaxies lie in their mass and velocity. This is mainly due to how black holes evolve over different mass scales. Black holes that are less massive grow primarily via mergers by coming together, the Agario model, even at low redshifts, while more massive black holes tend to grow via accretion, which is basically they eat more of the matter around them. Additional observations and improved measurements will help us understand these populations of young black holes, and further simulations will help us understand these different seeding scenarios for these early black holes as well. Woohoo! Well, thank you, Brandon Prius from Georgia Tech, for this amazing little article. So I hope you enjoyed that. I just wanted to give a bit more, bit more of a dive into some of the earliest black holes, and this was a really exciting one. The small ones come together and support each other, but some ones start off big and then make the switch. Yeah, no, exactly. Actually, yeah. Actually, that's one way to describe it. Comparing black hole models to VTubers, exactly. Woohoo! So that was basically all I had for today. If you guys don't mind, I'm going for a bit of a shorter stream, but I did want to end with, maybe we should just play a round of Agario. I hope this doesn't, like, dox me. I'm a little scared, but it'll be alright. We're gonna make this happen, Orbeez. Today's stream has been really scuffed, but that does not mean that we're gonna be stopped by Agario. Actually, let me see if I can try to refresh this. Oh. Guess there's this, like, weird black bar at the bottom. Yeah, let's do this! Okay. I'm gonna play as Z. Wait, I'm like a little scared that something's gonna pop up or something. Alright. Alright. Wait, what are the controls? Wait. Oh, okay, it's just my mouse. Okay, it's just my mouse. Okay. Okay. Black hole simulation time. When are we getting Z playing Katamari? What's Katamari? I actually downloaded this free horror game, actually. That might be a fun stream to do. OMG. I think I can eat this person. Okay, actually, no, never mind. Oh no! Ah! No! Okay, we're gonna do this again. We're gonna do this again. Oh my god. Oh my god, I'm like wedged between like 30 different things. The little dots are the stars. Well, it's actually probably more like high energy plasma, but I'm sorry, I'm way too nerdy. Highly advanced black hole simulator. Yeah, we don't need any of those, like, really advanced models to understand gravitational waves. We can just use this. Oh my god. I actually haven't played this game in a— Oh no! Okay. Oh my god, okay. I actually grew a little bit from that. Katamari is a game series that started out on the PS2. Ooh. I'd be happy to check that out. Actually, if you guys really enjoy this, maybe I should just have like one stream sometime just for like these kinds of games. I used to be quite good at Slitherio as well. I actually really enjoy these games. I used to play these a lot. Gario, but weirder. Ooh, there's a lot of plasma here. Please, I want to eat you. Okay, no. Oh, wait, this thing's a little bit too big for me. Oh my god. Oh my god. Okay, I'm like— Oh no. Oh shoot. Oh no. I guess I'm not very good at Agario then. It's so Zover. No, don't cry because it's over. Smile because it's Zappened. Alright, we're gonna play one more game and I think I'm gonna wrap things up because my because my voice is going out a little. Oh wow, I'm like really moving fast. Oh my god. It's like what Psy did to the waffles. Oh, that was actually one of my highlights this week. I really enjoyed this video of Psy eating waffles made by Eggy. Oh, and Syzygy also made like a music video. And I actually made like a bit of a cameo in it too. I was this quantum mechanics Pikmin. So Syzygy's song was on like Pikmin. And there were like different like scientific instruments. And there was like this one part where it was like quantum Pikmin. And then like there was a version of me, but like with like a pointy nose and like the Pikmin like leaf thing, and it was like me like spinning in space. It was hilarious. I was like, I was getting back from my travels and I was watching this video and I just like genuinely did not expect me to make a cameo. Oh shoot! Oh shoot! Oh shoot! I guess if you guys really like this, maybe I should do an Agario stream. Oh, I'm sorry, I meant Black Hole Simulator stream. Okay, come on, I can beat this. Oh, shoot. Come on. Shoot! No! Oh my god! Orbeez, I'm really bad at this. I guess I'm not a very good black hole. Whoa, Astral! Nice new profile picture. Oh, I guess Astral, you also stream as well. That does look like your streamer icon. No, this was great though. Oh my god. Yeah, there comes Ton, what was it, Ton 2808 or something? That's great. Well, let me quickly check to see if, let me quickly see if anyone is streaming. I want to raid into somebody, but I need to check my Twitch to see if, anyone is streaming. Actually, Nep is streaming right now. Do you guys want to do a cross... Yeah. Do you guys want to do a cross raid stream? Cross... What am I saying? Cross raid stream. Cross stream raid. Orbeez, I'm gonna take a nap after this. I'm still feeling under the weather. Let's do it. Let's do it. Alright, I'm gonna just hop on there and say Nep raid, Nep raid. Oh, wait, no. Z raid. Z raid. OMG. Orbeez, I'm so out of it right now. Anywho, that's gonna be all from me today. Thank you all so much for stopping by. I'm really glad you guys enjoyed this stream, and I hope you learned a little bit from Black Hole. I will see you guys on Sunday. Hopefully I will be less sick then, and for some exciting trolley problem with Millenium. I'm so excited, and my voice will hopefully be better then, and my OBS will not be as scuffed. So until then, thank you all so much. Everybody go hop onto Nep's stream. I will see you guys in the next one. Drink some warm tea, and be safe, y'all. And not sick. Bye-bye! See you later! See you later! Thank you for the well wishes as well. I will rest my voice now. Thank you. Bye-bye!